Hello, welcome to my presentation. I am Chen Ying, a PhD student from the Technical University of Munich and German Aerospace Center. Today, I'm going to present our recent work, Cross-modal pre-training with noisy labels for remote sensing image segmentation. Nowadays, we have been in the area of big geospatial data. With the increasing number of satellites launched, a plethora of satellite data modalities is becoming accessible. To cope with such big data, deep learning shows powerful capability to tackle many important tasks. However, deep learning models are notoriously data hungry. Training deep learning models requires a large amount of accurately annotated labels. But the annotation process of remote sensing data is generally expensive, laborious, and time-consuming, thus difficult to meet such a requirement. On the contrary, noisy or inaccurate labels are much easier to come by in low cost. There exist many easily available pixel-wise noisy label sources in the remote sensing domain, such as the OpenStreetMap, various land cover land use products, the labels generated by some automatic labeling tools, and so on. Deep learning models are capable to learn any complex function, so training deep learning models with noisy labels can easily lead to overfitting to label noise. Although the learning can be biased by the label noise to some extent, we found that deep learning models do exhibit a degree of robustness against the label noise. As illustrated on this slide, the encoder parts are less susceptible to label noise than the decoder parts. This is partly because more semantic information is encoded in the decoder, while the encoder, further away from the classification head, tends to learn more general and basic features, thus less affected by the label noise. Based on the above observations, in this work, we target at exploring the potential of pixel-wise noisy labels in pre-training for image segmentation tasks. We developed a new method called CromSS. Specifically, we investigate the utilization of noisy labels in a multi-modal learning framework in order to employ complementary information across different modalities. Furthermore, we designed two sample selection modules to exclude some cropped labels or low-confidence predictions. Notice that the two sample selection modules are plug-in modules, which means that they can be conveniently inserted into or removed from the multi-modal learning framework. Ahead of presenting the details of our proposed method, on this page, we first introduce the pre-training dataset we utilized in our work. The dataset is an extension of the SSL4EOS12 dataset. SSL4EOS12 is a self-supervised learning dataset without labels. It originally contains image pairs of Sentinel-1 radar and Sentinel-2 multispectral images globally sampled from 251,000 locations and 4 seasons. We paired non-class dense noisy label masks sourced from the Google Dynamic World Project on the Google Earth Engine for this data. As a result, we successfully paired 104,000 locations with noisy label masks for all the 4 seasons, and we utilized this data with noisy labels for pre-training tasks. Now we go to the methodology part. In our work, we tested two multi-modal pre-training architectures, late and middle fusion. The major difference of the two multi-modal frameworks compared with the single model case is the addition of the consistency loss across different modalities. Besides, we keep the modality-specific encoders for each modality to guarantee the encoder's flexibility when transferred to downstream tasks. Concerning the decoder parts, while late fusion uses separate decoders for each modality, middle fusion employs shared decoders to further boost cross-modal entangling. In terms of the sample selection modules, the basic logics behind them is to generate some sample selection masks to serve as the weighting matrix when we aggregate loss values from each sample or pixel. In the following, we will take the sample selection mask generation pipeline for Sentinel-1 as an example to uncover the details. To generate the sample selection masks, we first generate the confidence mask from the softmask outputs. Here, the softmask outputs can be regarded as the estimated probabilities of the model predictions. For segmentation loss, we utilize the estimated probabilities corresponding to the noisy label class as the label confidence value for each sample. While for the consistency loss, we calculate the entity confidence via the entropy of possibility vectors for each sample. After that, we do the cross-modal confidence enhancement with the confidence mask from another modality. In this example, here, they are those from the Sentinel-2 data. To do so, we multiply the confidence mask from the two modalities to serve as the modification mask. In this modification mask, the agreement can be enforced, while the disagreement can be moderated across two modalities. By averaging the modality-specific confidence mask and the modification mask, we can insert the cross-model information into the final confidence mask, and at the same time, to a large extent, maintain the modality-specific message within the final confidence mask. Finally, we generate the sample selection mask from cross-model informed confidence mask with the given threshold omega and the weighting factor gamma. Particularly, for the segmentation loss, we assign the weight 1 to one sample if its confidence is above the threshold value. Otherwise, we assign its normalized confidence value with omega as the soft weight. For the consistency loss, we use the weighting factor gamma to control the proportion of the entity confidence in the entity sample selection mask for consistency loss. In the experiments, we pre-trained ResNet50 nested in UNet with the proposed chroms for 100 epochs. The selection threshold omega is set according to the exponentially ramping down selection proportion from 100% to 50% for the first 80 epochs. The selection weighting factor gamma is at the same time ramping up from 0 to 1. We transfer the pre-trained backbones to the DFC2020 dataset with ResNet50 nested in the PSPNet framework. In comparison, we also present the results with single-model pre-training with noisy labels, multi-model pre-training with noisy labels yet without sample selection, as well as two self-supervised learning methods, Dino and Moco. The weights by Dino and Moco are provided along with the SL4EOS12 dataset using all the 251,000 data points in pre-training. Here are the transfer learning results obtained on the DFC2020 dataset. The frozen and fine-tuned in the table indicate different learning behaviors of encoders in the downstream task. Frozen corresponds to fixed encoder with only decoder updated, while fine-tuned refers to the weights of both encoders and decoders are adjusted. From the table, we can observe that the proposed chroms can improve the effectiveness of the pre-trained ResNet50 in remote sensing image segmentation, in particular for S2 multispectral data. Besides, the middle fusion strategy showcases a larger margin compared to the late fusion. This indicates that the implicit data fusion via decoder weight sharing can boost the learning across modalities to some extent. We can also observe some improvements of single model pre-training with noisy labels compared to Dino and Moco. These outcomes further demonstrate the potential of using noisy labels in pre-training for segmentation tasks. Then we show some sample selection masks. For comparison, here we list both the selection mask generated from the confidence mask before and after cross-modal enhancement. As observed, informing the label confidence mask of Sentinel-2 data with that of Sentinel-1 can reduce the uncertainty in the ice region within the final label selection mask of Sentinel-2 data for segmentation loss, while enhancing the confidence mask of Sentinel-1 with those of Sentinel-2 can lead to more detailed information for both consistency and segmentation losses. This example indicates the effectiveness of the cross-modal confidence integration in calibrating the single model selection masks. To conclude, we introduce a new pre-training strategy called CromSS, guided by noisy labels for large-scale remote sensing image segmentation. CromSS explores a cross-modal sample selection strategy to reduce the adverse effects of label noise. Transfer learning results on the DFC 2020 dataset demonstrate the effectiveness of the CromSS pre-trained ResNet 50 encoders. In future works, we will devote to further improve the effectiveness of CromSS on weak modalities such as Sentinel-1. We will explore the potential of CromSS for visual transformer pre-training and do some comparisons with masked image modeling pre-training. Moreover, we will also test CromSS on more kinds of noisy labels and noise rates to test its robustness. Thanks for your attention. Please feel free to reach out if you have any questions.